Hello everyone, my name is Ehsan Kazemivalipour. I will be presenting our work based on design of an imperfectly manufactured 8-channel transmit array coil using the equivalent circuit model. Our center received research grants from the ASASA. Transmit array or TxArray technology can be very critical for 3 Tesla systems since they can enhance field uniformity, increase power efficiency, and they can enable RF shimming and mitigating SAR hotspots. Increasing the number of independent transmit elements can enhance the TxArray coil's capabilities. However, for a higher number of array elements, the design complexity will increase. A variety of methods for designing TxArray coil has been proposed, all of which are in the simulation environment. For those TxArray coils that are manufactured imperfectly, most of the time the simulation results are not matched with the measurement results very well. Therefore, it's challenging to predict the optimum lumped elements of the manufactured coils. To overcome this issue, the vast majority of coil designers initially use the lumped elements values obtained from the simulation along with some added variables components. They perform fine-tuning process and attempt to reduce the difference between the simulation and experimental results. Fine-tuning of TxArray coils is hard as adjusting one transmit channel will affect the performance of other channels. The array elements need to be iteratively tuned, matched, and decoupled one by one in successive steps. Therefore, this approach is a time-consuming process, becoming more unfeasible when the number of array elements increases. In this study, we properly simulated and designed a TxArray coil, then we fabricated the coil by assembling the optimal lumped elements achieved from the simulation. We found that the measurement results are not matched with the simulation results. To reduce this difference, we modeled the manufactured coil using distributed lumped elements. Then we measured the impedance matrix of the manufactured coil to predict all unknown elements of the coil's equivalent circuit model. We adjusted coil's free design parameters integrated with the circuit model. Then we could finally design the manufactured coil properly only by one iteration. The proposed model and schematic of a TxArray coil at 3 Tesla with 8 transmit channels, which evaluated in this study, are shown here. In each loop, 4 distinct capacitor values mainly control the coil's performance as a free design parameters. By adjusting the coupling capacitors placed between the nearest neighbors, transmit channels can be decoupled. Due to the mutual capacitors between the neighboring channels, fine-tuning of this coil is very time-consuming, as adjusting one coil channel will significantly affect others. When the CP excitation is applied to this coil, it produces a B1 plus field similar to a conventional birdcage coil. The proposed coil with the same dimensions of the simulated coil was constructed. As the coil was not machine manufactured and therefore not quite the same as the simulated coil, we expect a difference between the simulated and measured S matrices if the same capacitor values used for both of them. This figure illustrates the manufactured TxArray coil's equivalent circuit model. In this study, the effects of all inductances and resistances emerging from the coil, shield, and load were taken into consideration. However, only self-inductances and resistances are shown in this model. By the assessment of the model with the Kirchhoff mesh current method, we can simply derive the coil's impedance matrix as a function of capacitors and frequency. L and R represent the inductance and resistance matrices. C, Cs, and Cm represent the capacitance matrices. They can be defined by the following equations. If all inductor, resistor, and capacitor values are known, the coil's impedance matrix can be obtained. Following 3 steps can enable us to predict all unknown elements of the coil's equivalent circuit model. First, in constructing the manufactured coil, the optimized capacitor values achieved from the simulation environment can be used initially. Then the impedance matrix of the manufactured coil over a wide range of frequencies should be measured. Finally, we can calculate the inductance and resistance matrices as a function of frequency, impedance matrix, and initial capacitor values. Once the inductance and resistance matrices are determined, a new set of optimal capacitor values can be obtained for the manufactured coil. The new impedance matrix, which fulfills the design criteria, can be measured by updating capacitor values used in the manufactured coil. In the design process of both simulated and manufactured coils, we adjusted the capacitors to minimize the Fallen cost function at 123.2 MHz, where in the first term, S matrix elements are minimizing to appropriately tune, match, and decouple all transmit channels. It should be noted that the first term can be interpreted as the ratio of total reflected power to the total incident power under single channel excitation, which can be called the normalized reflected power in the single channel mode. Including the second term minimizes the normalized reflected power of the CP excitation mode as a critical operation mode. For more details on this approach, you can check program 762. As iteration 1, the optimized capacitor values obtained for the simulated coil were used in the manufactured coil. The results show that all channels of the simulated coil resonate at the desired frequency with a reflection coefficient of less than -26 dB, which shows that they are very well matched and tuned. Unlike the simulation, the transmit channels of the manufactured coil resonate at different frequencies with different matching levels. The normalized reflected power in the single channel mode shows that its lowest value for the simulated coil is 0.23, which is attained at the desired frequency. On the other hand, for the manufactured coil, the lowest value is 0.47 at 131 MHz. Looking at S matrix for both simulated and manufactured coils at their resonance frequencies indicate all S matrix elements are different, which shows the manufactured and simulated structures are not identical. By applying the proposed approach to the manufactured coil, new quantities of the capacitor values were determined and updated on the fabricated coil. The results show that all transmit channels of the manufactured coil resonate at the desired frequency with an acceptable matching level, all less than -15 dB. The normalized reflected power in the single channel mode shows that its lowest value for the manufactured coil is 0.33, which is attained at the desired frequency. This value is a bit greater than the same simulated value, but still it is the lowest achievable number for the manufactured coil. The maximum coupling of the simulated coil was -10.7 dB. For the manufactured coil, it was -8.9 dB. For both coils, the maximum coupling was observed between the neighboring channels. However, for non-neighboring channels, the maximum coupling was -17.6 dB and -13.5 dB for the simulated and manufactured coils. Also, the normalized reflected power of the CP mode was 8% and 20% for the simulated and manufactured coils. To conclude, I should say that most of the time the simulation results are not matched with the measurement results very well because of the coil's manufacturing imperfection. The exact manufactured structure of TxArray coils may reduce this error and accelerate their design process. In this study, we developed a practical approach based on modeling of manufactured TxArray coils using distributed lumped elements. All magnetic and electrical couplings effects were modeled due to prediction of all inductance and resistance values. We evaluated the performance of an 8-channel TxArray coil in both simulation and measurement. The normalized total reflected power in the single channel mode and CP excitation mode were minimized. With only one extra iteration, we could properly design the manufactured TxArray coil. Thank you for listening.